Pascal's triangle is really nifty. There is a lot of mathematics involved in making the triangle, and many uses of every number in each row and column. It is a sequence of numbers created by starting at 1, imagining there is a 0 on either side, and then summing two numbers that are beside each other to create the next row. For example, it goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Do you see the pattern? This creates an infinite triangle of numbers that have special properties. What are the things we can learn from Pascal's triangle? The rows start at the 0th row. Here we have the first row, the second row, and the third row. Let's look at the third row. The numbers in the third row are 1, 3, 3, and 1. We know that these are the coefficients of the binomial expansion of x plus y cubed. This works for the fourth row and every other row too. Adding the numbers of each row, we can also see a pattern evolving. The sum of the row, for example row 2, we get 2 to the power of 2 equals 4. What about the sixth row? 2 to the power of 6 equals 64. This works for every other row also. Another cool trick is that each row sums up to that row's number as the power to 11. That is, if row number is n, the sum of the horizontal numbers is 11 to the power of n. But this doesn't work for row 5. This is because you have to treat each number as if it is in a different place value. For example, in row 5, we have to add together the numbers, and what is 11 to the power of 5? 161,051. Magic, hey? If we look at a descending column, the first is just ones, the second is the natural numbers, and the third is the triangular numbers. They form stacks of triangles. Similarly, the fourth descending column is the tetrahedral numbers. They form three-dimensional stacks of triangles.
Pascal's triangle can be useful for binomial expansions, to expand something such as x plus y to the power of 3. As a helping with binomial expansion, we see here x plus y to the power of 0 all the way to 4. Taking note of the power of the expression, it corresponds to the row in Pascal's triangle, and so the coefficients of the terms are the numbers in the row of Pascal's triangle. As you can see, for the power 1, the coefficients are 1 and 1. I wrote it down so you can see. For the power 2, we have coefficients 1, 2, and 1. For the power 3, we have coefficients 1, 3, 3, and 1. And for the power 4, we can see the coefficients are the same as the fourth row. As for the x and y factors, that can be explained as such. Say we have x plus y to the power of n. The power of x will start at n and decrease to 0, and the power of y will go the opposite way, going from 0 to n. It doesn't actually matter if you go the other way and have the x's power increasing and y's decreasing, as the coefficients from Pascal's triangle are symmetrical.
Although Pascal's triangle is named after the 17th century mathematician Blaise Pascal, multiple other mathematicians knew about and used their knowledge of the triangle hundreds of years before the publishing of Traité du triangle arithmétique in 1654, which comprehensively explained the properties of the triangle. The triangle appears to have been discovered independently by both the Persians and the Chinese during the 11th century. One of these 11th century mathematicians was Sin, whose work showed that he was using the triangle to extract square and cube numbers, thus prompting the Chinese to continue researching the triangle. Many years after Sin's discovery, a mathematician by the name of Yang Hu created the earliest known display of Pascal's triangle in 1303. Thus, Pascal's triangle and the use of its binomial coefficients were known long before the birth of Blaise Pascal.